So what Theorem 9 says, I actually just kind of want to review Theorem 8 because they both deal with composite functions. So Theorem 8, as a reminder, and you can take a look back at example 4, but that said if you had the limit as x approaches a of a composite function, so of f of g of x, you're really only taking the limit of the inside function, and then whatever value you get, you're evaluating the outer function at that value. So you can see that's what we had done here. We took the limit of the 1 minus square root x over 1 minus x as x approached 1. We found that limit to be 1/2, and then we found the value of arc sine or inverse sine of 1/2 to be pi over 6. So example 5 is very similar to that, which is why I'm skipping over to example 9, or to Theorem 9, and then underneath examples 6, A and B. So Theorem 9, this is also looking at composite functions, but saying where they are continuous. So not necessarily finding a limit of a composite function, but just saying where are these composite functions continuous. So Theorem 9 says if g is continuous at a and f is continuous at g of a, then the composite function f of g is given by one of these two notations, f of g of x, whichever way you like to write it, is also continuous at a. So just in words, a continuous function of a continuous function is also a continuous function. Now, that's very wordy. To actually determine where they are continuous, again, this is asking you basically to find the domains. So I'll review how to find the domain if you have a composite function. So with a composite function, you first need to look just at the inside function. So if we're looking at example A, we would be looking at the 1 plus cosine of x. And you determine first the domain of that function. So 1 plus cosine of x, any ideas where that would be continuous or what the domain would be? All real numbers. So cosine of x, domain is all real numbers. If you're just adding 1 to it, it's still going to be continuous everywhere. So this is continuous on the interval negative to positive infinity. If this had a restricted domain, a restricted interval for continuity, that would then restrict the overall function as well. So if the outer function was continuous everywhere, it would be restricted by the function that's inside. So we don't really have to worry about this because it's continuous everywhere, but now for natural log of this, remember that the domain for natural log, whatever's inside of a natural log function or any logarithmic function, has to be greater than 0. So for this to be continuous, the 1 plus cosine of x must be greater than 0 in order for the outer function to be continuous. So if I were to solve this inequality for x, this would mean if I subtract 1 from each side that cosine of x has to be greater than -1. And in thinking about this, I could certainly take inverse cosine of each side. But in thinking about this, the range of cosine of x is -1 to 1, where they're both included. So when I'm saying it has to be greater than -1, this is basically saying it just can't be equal to -1. So this is going to be undefined whenever cosine of x is actually equal to -1, because otherwise, still on its range, otherwise it's greater than -1. So at what angles, so at what x values, is cosine of x equal to -1? At 0, it's equal to +1. So pi or 3 pi or 5 pi. So thinking of, well, just so it's included on here, I'll just draw this up here. Thinking of the unit circle, So this would be the ordered pair 1, 0. Remember, cosine of the angle is your x value, and then sine. This is 0, 1. This is -1, 0. So this is where, or this is the angle at which cosine is -1. And that's pi or every multiple of 2 pi after that. So this would be when x is pi, or 3 pi, or 5 pi, or I could even go backwards, -pi, and so on. So I could write that as pi plus 2 pi n, where n is an integer. Question? Yeah.
So could you also just envision the graph of cosine?
Yeah. Yep, you could envision that as well, yeah. So then, how to write this? I know I said it's undefined when. So I'm not going to write this in interval notation because there's obviously going to be infinitely many separate intervals. So to write this, I would say it's continuous. I'll say f of x is continuous on, and I'll write this in the set builder notation. So the set including x, you could specify x as an element of the real numbers, but we only work with real numbers in calculus. So x such that x doesn't equal pi plus 2 pi n. And as long as, if you had, I know I kind of talk, anytime I'm saying, or talking about work, I'm kind of thinking ahead to how you would show this on the AP test. As long as you said in your work that n is representing an integer, if you don't say it again here, that's okay, as long as you have it written somewhere. But again, it's continuous on its domain, and that would be the domain for that function. For integer, it's a z, where the middle is kind of that double. So yeah, you could add after this, n is an element of the integers, to show n is an integer. You get super fancy. No, you don't get extra points for that. No. There's no extra credit option. That'd be nice, but there isn't. So if we looked at B, I included A. I mean, this is a little more complex, picking out those angles. I know, just kind of reviewing that trig. I don't just set aside time to review all of the trig. We just kind of review it as it comes up. So it's not trig heavy, I would say, but it comes up every so often. I realize this is also a trig function, sine of x squared, but it's a little bit easier to understand. So here, x squared is inside of the sine function. So I'd first think about, where is x squared continuous? Are there any restrictions? So x squared, no, is continuous everywhere. And then the outer function, sine, does that have any restrictions? On the domain? No. Sine of, if it was just sine of x, it would also be continuous everywhere. So I'm just going to make a note, sine of x, and that could be sine of any quantity, is continuous everywhere. So therefore, our function h of x is continuous on the interval negative to positive infinity, or is continuous everywhere. So we've kind of already done some problems like this. I think when we went through domain, there weren't a ton of composite functions, but again, it's finding the domain. That's what finding an interval of continuity is really asking you. What is the domain of the function? Questions? Okay. Were there any questions? If anybody looked at this practice yet, were there any questions you'd like me to go through at this point? Certainly, there'd be time tomorrow, too, if you haven't looked at everything, because we hadn't quite finished, but number 19. Okay. 17, which ones were you assigned? 17, 18, 19, and 21. We're all asking the same thing. And it said, this is why I included the numbers of the theorems in the notes. It said, explain using theorems 4, 5, 7, and 9, why the function is continuous at every number in its domain. Theorem 4 was where you're combining functions, so adding, subtracting, multiplying, or dividing, or multiplying by a constant. 5, oh, that was the one that said polynomials, rational functions are continuous on their domains. 7 was the theorem that said basically every other function we work with is continuous on its domain. And then 9 was the one we just covered, so we hadn't quite talked about that yet. But how I would break this up, so it says explain why and then state the domain. And you don't necessarily have to explain with the specific functions. I think I wrote out the solution for 18 that was posted. But I can see that f of x, first of all, is a product of two functions. So that would be using theorem 4. I would find where e of x is continuous and then where sine of 5x is continuous. And then their product of the two functions would also be continuous. So if I break this apart, where or on what interval is e to the x continuous? There are two different answers. So e to the x, the domain is all real numbers. The range would be all positive numbers. So e to the x would be continuous on the interval all real numbers. This would technically be using theorem 7 because it says exponential functions are continuous on their domains. And then sine of 5x. So this is actually kind of using, what we just used, the theorem 9. So 5x is technically inside of the sine function. 5x is a polynomial. This is continuous on all real numbers. And then we know sine of x is also continuous on all real numbers. So therefore, sine of 5x would be continuous on all real numbers. And then with the product of the function, so you'd want to see where the two domains or intervals of continuity overlap, and that would be all real numbers. So overall, f of x is continuous on all real numbers. So I realize the directions, maybe this could have thrown you off if you looked at it. I'm not expecting your explanations for you to say by theorem 4, because the theorem 4 was named by the textbook as just, it's the fourth theorem we're talking about, either in this section or in the chapter. I'm not sure exactly how they have it set up. But it doesn't have a specific name. So the theorems are there, which is fine for you to just have an understanding. Exponential functions are continuous on their domains and so on. Does that help for 19? Okay. Were there other questions? '21 might be similar to one of the examples we just did. G of t. Yeah. So yeah, this would be like example 6a that we had done. So first you look at the t to the 4th minus 1. Are there any restrictions on that domain as that function? No, this is continuous everywhere. However, for the natural log function, the t to the 4th minus 1 has to be positive, greater than 0. So this means if I solve for t to the 4th has to be greater than 1. And if I take the 4th root of each side, remember again, if this was an equation, I would say t is equal to positive or negative, but I can't use that same reasoning with inequalities. So I would say the absolute value of t would have to be greater than the fourth root of 1 is still 1. So this means t is not in between negative and positive 1, but it's greater than 1. So if you think about it, the absolute value of t has to be greater than 1. So that means t value is greater than 1, but also t value is less than negative 1. Because values like -2, -3 would still have an absolute value that's bigger than 1. Does that make sense? This is going back to algebra when you solve an absolute value inequality. If you remember, great or and then less than. So this is where, because it's a greater than symbol, it's equal to a compound inequality that's or. The first inequality is as if you're not changing anything. The second inequality, the sign changes. The inequality switches and the sign of the number changes. But the reasoning, hopefully that makes sense. So this would be, and this then combined with all real numbers would mean this is just your interval for continuity. So if I put this in order, it would be -infinity to -1, not included, union, and then 1 to positive infinity. And you could even try that out. Those are the values if you substituted in for t that would make inside the natural log function positive. Does that help for 21? And then 29 you said? And you did not have to sketch the graph. If you really wanted to, you could, but you didn't. And then after this, if you still have questions, we need to get to the activity. Like I said, we'll have enough time to look through it, but I at least want to get to the activity. All right, this was 29, and it said determine where this function is discontinuous and at which of these points is f continuous from the right, left, or neither. And then it said to sketch a graph, which you don't have to do. So we didn't go through these problems yesterday, but we've been through examples like this. When you have a piecewise function, what are the values you should check for being discontinuous? Yeah, approaching from the left or the right. Yeah, look at your boundaries in these domains, the 0 and the 1. Those are where your expressions change. Those are the possibilities or the candidates for being discontinuous. So you should check at x equals 0 and at x equals 1. And to check that, you're seeing, again, for continuity, does the actual function value exist? So that we can see because there is a place where the x value can equal 0 and can equal 1. But does the function value exist? Does the limit exist? In which case you have to check from the left and the right for the limits. And then do they equal each other? So is it okay if I show at 0 and then you could apply it and check at 1? You can at least get a refresher how to do this. So at 0, I still want to find the function value because that's going to tie into whether or not, if the limit does exist, does it actually equal the function value? So I would want to find f of 0. So I'd be looking at the domain where x can equal 0, meaning it's substituted into e to the x. So e to the 0 is just 1. So f of 0 is 1. And then because I have that break at 0, to find if the limit exists, I need to find, does the limit as x approaches 0 from the left and then from the right, are they equal to each other? So does the limit exist? So from the left, so values less than 0 would be using x plus 2. So I'd be approaching 0 from the left for x plus 2. So that limit, now I can substitute 0 in, would just be 2. And then from the right, I'd be using values bigger than 0, but still close to 0. So this middle expression, e to the x, if I substitute 0 in, that's 1. So does the limit exist? No. So it's discontinuous then at x equals 0 because the limit as x approaches 0 of f of x does not exist. However, at the x value 0, could we say it's continuous from the right or from the left? Or is it discontinuous from both sides? From the right, because limit and the function value are equal. So in addition to this, I realize I'm not writing complete sentences here, continuous from the right, and that's because the limit as x approaches 0 from the right of f of x equals f of 0. And again, I can't stress enough that you're actually using the notation, writing out the limits when you write your explanations. If anything I took away from that conference I went to this year, it was that they look for that. If you don't use it, you're not getting the points. So make sure you use it, the notation, yeah. So rather than putting into words the limit doesn't exist, they want to see that you're actually using the notation. So get used to using that. I'll be stressing that all year.